Okay, question 9, the first part of the multiple choice section for the year 13 PPE, January 2018. We're told in the first part that we're going to have a look at specimens Y and X, or X and Y if you prefer it that way. The stress versus strain graph. They're both stretched until they broke. That becomes important in a moment. So we're going to have a look at them and we're going to figure out which of the following is incorrect. Careful with that. We're looking for something that is wrong. Don't pick the first thing that you spot that's right and then just go on straight on. It's easily missed, this little bit. So what have we got? We've got these two graphs here. First of all, X is stiffer than Y. Let's have a look. That is true because it's got a steeper gradient. X has a higher value of the Young modulus. Again, true because it's got a steeper gradient. X is more brittle than Y. Well, when we talk about brittleness, we talk about something breaking before it gives. So if we have a look at this graph here, we see no giving at all. It doesn't sort of flatten off and give us loads of strain without increasing the stress. It just breaks. So Y is going to be brittle. X gives a bit. It curves a little bit. So we know that Y is going to be more brittle than X. So it's going to have to be C for this one here. Just to check, Y has a lower maximum tensile stress than X. You can see that X has a high maximum tensile stress because it can cope with more stress. It goes higher on that axis. So it has to be C for question 9. Now question 10 is along a similar sort of lines. We have 4 bars here, A, B, C and D. They're all made of the same material, so that means they all have the same Young modulus. That will be useful in a minute. Which bar has the greatest extension, A, B, C or D? Okay, well, with a question like this, you've got to think about what you have been given and what you're trying to solve. So we know the lengths, or the original lengths, the initial lengths of these things, either L or 2L. We know the diameters, and therefore we can figure out the areas. And we can see that we're given the widths as well. So if we think about our equation for Young modulus, we can see where all those things come in. The Young modulus is the stress over the strain. Stress over strain, well, stress is going to be force divided by area. It's the amount of force applied to every square metre of area. And then the strain is the extension divided by the original length. And we can rearrange that. Take the dividing by A to the bottom here. Take the dividing by L to the top here. We end up with FL over A delta L as our expression for the Young modulus. You've seen that written many times before. Now we're trying to work out which one has the greatest extension. We're going to try and work out how big delta L needs to be. So if I know that E is FL over A delta L, then I can do a bit of rearranging. Multiply both sides by delta L and divide both sides by E, and I'll end up with this equation here. Delta L is FL over AE. So the extension is the force times the length divided by the area and Young modulus. So let's have a look. Well, they've all got the same Young modulus because they're all made of the same material, so we can completely ignore this E thing. We're not going to have any difference between the 4 materials for that because it's all the same. So we've got to figure out now what's going to happen when we start messing around with the dimensions and the forces on these bars. So here's our first one. Let's just go through them all and compare them to the first one. Probably the easiest way. So this one here has got twice the diameter and it's got twice the force acting on it. So the force is twice as big. But if the diameter is twice as big, then the area is going to be 4 times as big. Because, I mean, if it's, for example, it doesn't really matter, but if it was a circular rod or bar that we're looking at here, the area will be given, of course, by pi r squared. So if we double this r, it now becomes pi 2r all squared, which is going to be pi times 2 times 2 times r, which is pi times 4 times r squared, which is 4 times the initial value. So if you double the radius, you quadruple the area. That's something that we've seen several times before, and it's going to be that fact that's going to help us to work out what the answer is. So let's go for it. This one here, twice the force, because we've got 2W, but if the diameter is twice as big, we're going to have 4 times the area. So if this thing gets twice as big, this F, but the area gets 4 times as big, then the overall extension is going to be less. In fact, this is going to stretch half as long as this one does. Let's use the same logic to work out for C and D. So C, let's see, it's got twice the length. So again, we've got a factor of twice the length here. The weight is the same, so this doesn't change. Again, the diameter has got twice as big, so the area is going to be 4 times as big. So this is going to be 2 times as big, this is going to be 4 times as big. The overall effect on delta L is it's going to be half as big. So this one's going to stretch by a certain amount, this one's going to stretch by half that amount, that one is also going to stretch by half the amount. Okay, what else have we got? D, the last one. This has got 3 times the diameter and 3 times the weight. Hopefully you're seeing where we're going with this one. 3 times the diameter, that's going to give us 9 times the area. So A is going to get bigger by a factor of 9. The force has got bigger by a factor of 3, so 3 times as big for F, 9 times as big for A. The length, of course, is twice as big when we're comparing it to A. So if this F here is getting a factor of 3 times bigger, and this is getting twice as big, and this is getting 9 times as big, then we're going to end up with basically 6 times as big at the top, 9 times as big at the bottom. It's still going to be smaller than this one. So the answer is actually going to be A for question 10. Bar A is going to stretch the furthest compared to the others. Question number 11. Let's go with that. There we go. Okay, the least distance between 2 points of a progressive transverse wave which have a phase difference of pi by 3 radians is 0.050 meters. A situation like this, we kind of need to see it in real life, so let's draw ourselves a bit of a sketch. 2 points of a progressive transverse wave with a phase difference of pi by 3 radians. Well, you're thinking, well, here's my wave here, we'll just draw one wavelength there. Now the full wave has got, let's move that into the screen, it's got a 2 pi radian difference between the very beginning of the wave and the very end of the wave. There's 2 pi radians phase difference in between those two. So if we're looking at pi by 3, well, that's a sixth of 2 pi, isn't it? So we're looking at a sixth of the wave. So I guess if this is about halfway along, it's kind of about this way. There we are. It's about a sixth of the wave. We're looking at these 2 points here, so this point here, this point here perhaps. We're told that that distance is 0.05 meters, or 0.050 meters. That will be important if you have to worry about significant figures, of course. So if a sixth of the wave is 0.05 meters in terms of its length, then the full wavelength is going to be 6 lots of 0.05. So the wavelength is going to be 6 times 0.05 meters, which is going to be 0.3. There we go. So we've got a wavelength of 0.3 meters. We've got to figure out what the speed of the wave is, and we're told that the frequency of the wave is 500 Hertz. Let's stick that onto the screen for you. There it is. So we know the wavelength, we know the frequency, and we know an equation that thinks frequency and wavelength times the two together. 0.3 lots of 500 is going to give you 150 meters per second, which is C. So 11 is going to be C. Question 12. Which of the following statements about stationary waves is true? Okay, well, this is where we could do with animation of a stationary wave. Yeah, it'd be just brilliant if we could actually get this iPad to work. Oh, look at that. There we go. Alright, so you've seen this in class before. This is the Desmos animation. I think for the sake of clarity, let's get rid of the two waves that produce the stationary wave, and let's just look at the stationary wave itself. So here it goes, up and down. So all of these questions about the properties of stationary waves. Let's see which is true and which is not. So it says particles between adjacent nodes all have the same amplitude. Well, that is obviously cobblers if you have a look at these. So I could take 2 points between two adjacent nodes. Let's take this node and this node. And as they come up, I mean, you can see this one, this point here, for example, is going far less high than this one. So these points are between two adjacent nodes, and they do not have the same amplitude. The one in the middle has got the biggest amplitude, and then the amplitude decreases as you get closer to the node here. Particles between adjacent nodes are out of phase with each other. Let's see. Well, here's an adjacent node here. Or between these two adjacent nodes, that's probably the best way of describing it. Let's have a look. So let's take these two particles, let's see, and they are in phase with each other. You can kind of see them coming down here. It's difficult to do this and keep an eye on the webcam at the same time, but if you look at these two particles, two imaginary particles there, they're both moving up at the same time, they're both moving down at the same time. So they're in phase with each other. So it can't be B. You may remember the general rule that if you've got two particles and they're either between adjacent nodes or there is an even number of nodes in between them, then they are always going to be in phase, and if there's an odd number of nodes in between them, they're out of phase. So if both of them are between the same adjacent nodes, they are going to be in phase. Can't be B. Particles immediately on either side of a node are moving in opposite directions. Well, you can just see straight away that that is going to be true. So these are two particles that I'm just pointing at here. As one goes up, the other goes down, and vice versa. You can see them going like that. So it's got to be C for 12, and just for the sake of completeness, there's minimum disturbance of the medium at an antinode. Well, if you know what an antinode is, that can't be true, because an antinode is basically defined as this point here where we've got maximum disturbance. Blech. Cannot talk today. Good, so it's going to be maximum disturbance rather than minimum disturbance. It can't be D. We already proved it was C anyway. Question 13. Copper metal is a good conductor because copper atoms in the metal what? This comes down to your idea of what's going on inside the copper. The copper is a conductor, it's a metal, it's basically a soup of free electrons moving around all over the place. All these delocalized electrons, and then you've got all of these positive ions that are kind of left by the electrons. If you're struggling to remember this, just go back and have a look at your ideas of conductors and semiconductors and insulators way back at the beginning of the electricity unit in year 12. But the general idea is that they've lost an electron, they leave behind positive ions and free electrons. These ones here, not quite so true. So gained a free electron, they haven't gained electrons, otherwise copper would have an overall negative charge. They're not ionised, otherwise the copper would be a plasma, which would be rather awkward to plug in. Negative charge because the free electrons, again, they don't have a negative charge, they haven't gained extra electrons, it's just that you've got a kind of splitting, so you've got the ion is left behind, the electron moves away, you end up with a positive ion here, your electron over here, which can then drift off wherever it likes. But basically 13D is the best way to describe your situation with copper. Question 14. Okay, so we've got a circuit in figure 1, PD is changing between the terminals of a cell, and we're changing the current, and we're looking at how V changes, I changes. We've got here a kind of potentiometer, potential divider kind of situation here, sort of. Often we'd have it plugged in like that, wouldn't we? But that doesn't really matter. So which of the following can be deduced from the gradient of the graph? Well, I mean, this takes you right back, hopefully, because whenever we looked at internal resistance, we had this sort of classic graph that helped us to work out exactly what the internal resistance was. In fact, it was a core practical that you'd have done for that one. So it always looks like this. So you've got your current here, doesn't necessarily have to intersect the axis there, current in amps, there we go, PD in volts or voltage in volts, and it's always the case that it intercepts here at the EMF, and the gradient you're going to get by V over I, which, if you're thinking about it, it must give you some sort of resistance, because Ohm's law says that voltage divided by current is resistance. It's going to give you the negative of the internal resistance, and the reason of that behind all of that is that the EMF is equal to the voltage supplied to the circuit plus the lost volts. So if we do a bit of a rearranging to work out what the graph of V against I is going to be, we end up with V is going to be epsilon minus IR. So we could rewrite that as V is equal to minus R times I plus epsilon. So this is your Y equals mx plus c kind of graph here. Gradient is going to be minus R, and the intercept is going to be epsilon, or the EMF. So here's your EMF, here is your internal resistance. Now if you're remembering all that, this is going to be dead easy, because it says what can you deduce from the gradient of the graph you're looking at. You're thinking straight away voltage against current, EMF kind of thing. We're looking at an internal resistance, so it's got to be A, 14A. If you're familiar with your content, that's not something for you to work out, that is just an answer for you to pretty much straight away recognise and write down. Nice straightforward one, time saving one on the exam. Question 15, nuclear binding energy is, and again we've got 4 explanations, but pick with which one fits the best. Wow, words are difficult today. I'm never going on holiday again. The energy required to overcome the electrostatic force between the protons in the nucleus. No. Because nuclear binding energy also, for a start, takes into account the force that is holding the neutrons together, and that obviously wouldn't include or be included in that statement there. And anyway, it's not really about overcoming the electrostatic force, it's to do with the energy linked to the strong force that holds these particles together. So it can't be A. Remember, when you're talking about nuclear binding energy, we're thinking about the amount of energy. You can think of it in terms of the energy required to sort of separate the nucleons. That's the idea. Energy equivalent of the mass of the protons in the nucleus. Again, you're ignoring the neutrons for no reason, and it's not to do with the total mass of the protons anyway. Because again, you may remember from the ideas of mass defect, the nuclear binding energy is related to the mass defect. It comes from the fact that when you take your nucleons separate and then you put them together, if you weigh them, or if you find their mass to be more specific, their mass is slightly less now. They've released some energy, and it's that binding energy that has been released. So we haven't converted all of the mass of the protons, or indeed all of the mass of the neutrons, so it can't be B. Energy equivalent to the mass of all nucleons in the nucleus. Again, same reason. Can't be their total mass, because not all of the mass of the particles is converted into to energy when you form a nucleus. Otherwise, there wouldn't be any particles left. All you'd have is energy, and that would mean that you couldn't have any atoms, and that would be bad. It's got to be D then. Let's have a look. The energy equivalent of all the difference between the total mass of the individual nucleons and their mass when they're contained in the nucleus. So you take all your particles out here, separate, you put them together, and you look at the difference in mass between them, and then the nuclear binding energy is equal to the equivalent energy from that mass defect. You can work it out via the famous equation E equals mc squared. If you take the mass that you've lost, the mass defect, multiply it by c squared, you'll end up with the energy, the nuclear binding energy. Question 16. We've got your classic binding energy per nucleon graph here. This should be very familiar to you. We're going to work out the approximate total binding energy for a nucleus of 184.74 tungsten. But it doesn't matter if you don't recognise that as tungsten. Right, so first of all we've got to figure out what's the energy from this axis here. So we've got to figure out how far to go. You'll notice that tungsten W is not on the labelled parts of here, so we're going to have to read it off. It's got 184 nucleons. This top number is the number of nucleons. So we're going to go all the way over here, 184, it's about there, roughly. Now I don't actually care exactly where we're looking at here, for a couple of reasons. Number one, if I move fairly far on this axis here, it's not actually giving me much of a change in terms of the y-axis. So I don't worry about it too much there. And number two, I've already had a cheeky look at these answers and found that they're all quite different. So that's making me think I don't need to worry about being exactly precise about, you know, getting my ruler out and measuring exactly where I think 184 is, even if I do have a very shiny ruler. I could read it off there. Yeah. Basically, it's 8 is what we're looking at. So we're looking at 8 as the binding energy per nucleon mega electron volts. Now, obviously, 8 isn't on there. So even if you thought that was the right answer, you'd be thinking, I've got to do something else with that number. Well, first of all, it's the binding energy per nucleon. And we've got 184 of the suckers. So if we've got 8 mega electron volts per nucleon, and we've got 184 of them, we can figure out how many mega electron volts we have. I just drew on my thumb. Sad times. Okay, so 184 nucleons, and each of them has got 8 mega electron volts. There we are. We're going to end up with a total of 1,472 mega electron volts, roughly. Let's get our thing back in. There we go. So 1,472 mega electron volts. Now, again, none of those answers are there, which is nice of them because they could have thrown that in as an answer just to trap you. There's one final thing you've got to do before you can have the actual answer, because this is in picojoules. So we've got to convert our mega electron volts into picojoules. Now you might know straight away that's 1.6 times 10 to minus 13 joules in a mega electron volt. I tend to do it in stages, if I'm honest, just to be entirely safe. So I remember that the factor to convert between electron volts and joules is 1.6 times 10 to the minus 19. You'll recognise that as the amount of charge on the electron. And just as an aside, this is coming from the equation where we say the potential difference is the work done per unit charge. So therefore we can rearrange that to give W is equal to Q times V. And the whole point of the electron volt is that if you take one electron and you put it through a potential difference of 1 volt, how much energy are you getting? Well, if I take one electron, it's going to have a charge. The Q is going to be 1.6 times 10 to the minus 19 if we ignore the negative sign, multiplied by 1 volt. So that tells us that we've got 1.6 times 10 to the minus 19 joules. That is equal to 1 electron volt. So if we're going to try and convert these mega electron volts in here, again you can work it out by equation, or you can just work it out by logic. If this tells me that my electron volt is a very, very small thing, so I'm thinking I'm either going to multiply or divide this by 1.6 times 10 to the minus 19. If I'm expecting to get a very small value for the number of joules, I'm going to need to multiply this number by this tiny number here rather than divide. So let's see. So that's 1,472. It's mega, so that's times 10 to the 6, times a factor of 1.6 times 10 to the minus 19, and that will give us, just get rid of all of that there, so 1,472 times 10 to the 6, I'm going to multiply that by 1.6 times 10 to the minus 19, there we go, 2.35 times 10 to the minus 10 equals 2.35 times 10 to the minus 10 joules. Okay. Now, I mean, looking at these 4 options here, it should be pretty clear straight away that the answer is going to be D. But if you still weren't quite sure, or if they didn't give you the 4 options, your stage at this point, if you've worked out in terms of joules, the last thing to remember is your SI prefixes. So milli is times 10 to the minus 3, micro times 10 to the minus 6, nano times 10 to the minus 9, and finally pico is times 10 to the minus 12. There we go. So if I've got 2 times 10 to the minus 10, that will be 200, this is basically 235.52 times 10 to the minus 12. So it's going to be 230 picojoules, and there's your answer D. We went into more detail than you would necessarily need to in the exam, of course. This is a multiple choice question, you've not got to write any working down at all to get your answers. Question 17. Moving on. Okay, we've got 4 objects. Which of the bodies is in equilibrium? Okay. Right, so we're told that each of them is 2 centimeters long and 1 centimeter high. We could figure out exactly the total force on all of these things. But it turns out there's a bit of a shortcut we can use by basically ruling out as many as we can. So this one, for example, if I took the moments about this point, I've got a force pushing up here and I've got a force pushing down here. There's going to be an overall clockwise rotation about the central point, so therefore it can't be in equilibrium. What about this one? This one could be. I've got a force upwards and then I've got a component of this force downwards. I've got a force to the right and a component of this force to the left. If I took moments about any of these points, it looks like I'd have a clockwise and anti-clockwise to cancel each other out, so it could well be that this is in equilibrium. Now, to figure out exactly whether this is in equilibrium or not, I would need to do a bit of trig. So I'd need to use the fact that I know exactly how big this thing is. It's 2 centimeters by 1 centimeter, so therefore this bit here, if I was going to split that up there, so we're looking at this thing here, the direction where this force is acting, I need to know where that is because it's going straight through the centre there. It's going to be 0.5 centimeters tall, it's going to be 1 centimeter wide. From there I can figure out how big this angle is going to be using a bit of trig, and from there I can figure out how big this component of this force is going to be. Ooh, that was a bit terrible, but luckily it was off camera, so I don't think you saw. It's as if nothing happened. There we go. So you can figure out how big this component of the force is here, compare it, or have a look at how big this component is as well, and compare it to the forces sort of going that way and that way. You could do all of that, and you could figure out, and it will turn out that the vertical component of this force here is 2 newtons downwards to cancel out this 2 newtons upwards, and it'll also turn out that the horizontal component of this force to the left will be 4 newtons in order to cancel out this 4 newtons to the right. You could do all the maths, but it turns out that if you look at these two, they are clearly wrong. So the easiest way is just to eliminate the wrong answers. We've already eliminated this one. Why can't this be true? Well, because there's no downwards force, but there's upwards force. So there's a component of upward force here. This is all upwards. There's no downwards. This can't be right. Okay. You could do the same incidentally with the right hand forces. Loads of force right. There's a component right there. No left force. This cannot be in equilibrium. And finally, all of the forces here have some sort of upwards component. No downwards force anywhere, so it can't cancel there. So this one isn't in equilibrium either. So all of these three easily annihilated, eliminated. This one you could figure out mathematically, or you could just figure out that all of these have gone, and that's the only one left. There we go, question 18. Now we have 2 charges, plus Q and minus 2Q, and we're going to figure out the electric potential at point P. So this is where we're going to need to bring in our electric potential equation. Electric potential, as you've been told many a time, is a scalar. So to work it out, the total electric potential, we're just going to add them together. So let's see if we can do that. So the total electric potential V is it can be V1 plus V2, where V1 is the potential from the first charge, and V2 we'll call the potential from the second charge, just to be nice and original. So V1 is going to be, we've got the equation for potential is Q over 4 pi epsilon naught R, and then the potential for the second one is going to be the same. It's going to be the second charge plus 4 pi epsilon naught R2. So all we have to really do is substitute the values in, and one of the answers here is going to drop out. So let's have a look at what we've got. So we're going to stick it onto the screen a bit better. There we go. So for this one, the first charge is going to be plus Q. Kind of running out of space here, so it's going to be Q. There we go. Over 4 pi epsilon naught, and then the distance, well, the distance to point P is going to be 2r, isn't it? We've got a distance of 2r there. So charge of plus Q, distance of 2r between this charge and this point here. 2r, there it is. And then we're going to add the second charge, which you'll notice is minus 2q. So we're going to stick minus 2q there. And then we've got 4 pi epsilon naught, and we've got to stick in the distance, which of course is just r. There it is. So at this stage we just need to thrash out the algebra. Let's see, you know what, I might bring in a second board. There we go. Okay, so we're going to try and combine these two things here. The easiest way to do that is to make their denominators the same, and then you can just add together these bits at the top. So let's see. This one's bigger. Let's double both ends of this and see where that gets us. So we're going to have Q over 4 pi epsilon naught 2r plus, and we're just going to, as I say, I'm going to double the numerator and the denominator, so we end up with the denominator being the same as this one. So we're going to end up with minus 4q all over 4 pi epsilon naught 2r. Okay, so we just doubled the numerator and the denominator. Now we've done that, we can add these two fractions together because they've got the same denominator, and we're going to end up with minus 3q, because I've got q minus 4q, all over, let's see, both of them, we've got the 4 and the 2 there, so we might as well take that out, so it's going to be 8 pi epsilon naught r. So hopefully, if we have a look at our options, we'll find that one of those is minus 3q over 8 pi epsilon naught r. I can't even see it, there it is, 18a. That's the one. And that's it. Your final question is question 19. Well done if you're still with us. Question 19. We've got parallel plates. Oh, this is exciting. This is the easiest question there, provided you know one little rule. We've got a minus charge here. It's in between, well, it's basically going from x to y, separated with a distance d. As soon as you're looking at these parallel plates, you're thinking, huh, uniform field. I wonder if that's going to be relevant. In actual fact it is, because you've got to tell me what the overall force is and how it changes as you move around in your uniform field. Well, here's the thing about uniform field, the force doesn't change, does it? So we're looking for a graph that shows me constant force. It's going to be this one. No working out required on this question at all. As soon as you look at this and you think uniform field, you're thinking the force is the same everywhere. You're thinking it doesn't matter what the distance is. The distance is not going to affect the force at all. It's just like if I took this pen and I dropped it at various points and places in my room. I'm going to find it has exactly the same force acting on it. It's got exactly the same gravitational force, because the field strength everywhere in my room is pretty much the same. We're in a uniform field. Of course, if I went outside and started launching this into space, it would start to decrease. because we wouldn't be in a uniform field anymore. We wouldn't be able to approximate having a uniform field. But anytime you've got a uniform field, here's the point: the field strength is the same everywhere inside it. So the field strength everywhere in here is the same. So the force on this charge, no matter where you are in between these two plates, will always be the same. It'll always be, well, it's a minus q charge, so it'll be always being attracted to the positive plate, repelled from the negative plate. There's always going to be a force that way, and it'll always have the same size. So it has to be 19C.